Hello, my name is Carter Ray. I'm a PhD candidate at the Université de Montréal. Today I'm going to be discussing with you a presentation that I recently gave at the ICM conference in Copenhagen in August of 2022. So I'm going to show everybody here the new paradigm of X-ray spectral analysis that we've been developing, where we use machine learning techniques to deconvolve X-ray spectrum. So with that, I'm going to get started, and I wanted to start off by demonstrating what the observations of the ICM actually look like in X-rays and what we would like them to look like and hope that they would look like. And I'll also explain why we don't get to see exactly what we would like. So what do we observe? Here I have a mock spectrum created using the Chow software, assuming a standard thermal model, the APAC model, and it's been convolved with the response matrix of the Chandra telescope and the ACES I instrument on Chandra. And you can see here that there's not a whole lot of features, right? It's very difficult to pull out individual features from this, and that's mainly due to the response matrix. So, what does the actual spectrum look like? What is the intrinsic source spectrum? Well, this is what the mock spectrum looks like before we do that convolution with the response matrix. So, before we take into account how the telescope actually collects photons. And our goal with this work is going to be taking these observed spectrum and the response matrix, which we know for each observation, and inverting that, doing a deconvolution to find these true spectrum. This has never been done before. It's been tried to People have tried to do it, and it's a very difficult problem computationally, and I'm excited to share this new method with everybody. So, very briefly, how does this look like mathematically? Well, you can describe your observed spectrum, and you want to compare it with your true intrinsic spectrum. This is a convolution problem with the response matrix of the telescope. We can reformulate this integral equation as using linear algebra as a simple matrix multiplication, where we again now have a vector of the observed spectrum. We have a vector describing the true intrinsic spectrum, and our deconvolution turns into a matrix multiplication problem where our response function is now a nice response matrix. So this is that very standard AX equals B matrix equation where we have the observed, we have this response matrix, and we want to solve for the true spectrum. You can try to invert it. You can try a lot of different techniques. I know we did. You can check out our research note, Ray et al. 2021, where we tried a bunch of standardized techniques to do this, and they unfortunately all fail for reasons described in the paper. So, how are we going to try to do this problem? Well, we're going to be using what are known as recurrent inference machines, which are very interesting and complex machine learning algorithms that effectively allow us to solve any linear equation, ax equals b, iteratively by using a neural network to update our solutions. I'm not going to go through the how these neural networks work. There's just not enough time, but look for future posts. I plan on writing one about the mathematics behind it. But how does this work in practice? Well, in 2017, this methodology was developed by a group of computer scientists showing how powerful it could be for solving linear equations when you have very ill-solved or ill-posed problem, very singular matrix. That's exactly what we have. Our response matrix is very ill-posed, and the first time and really only other time it's been used in astronomy is to deconvolve images. Those are ALMA images. So you take a dirty ALMA image, and you can, instead of using normal techniques that take an extreme amount of time and aren't always the most accurate, you can use this recurrent inference machine to actually do your deconvolution for you, and that's exactly what we're seeing here. So we decided, well, this is the beautiful 2D analog to our problem, so why don't we give it a go? Just to remind you, this is what the X-ray spectrum would look like. Keep in mind we have the response matrix. And what we'd like to do is recover this green curve using our recurrent neural network, or really using our recurrent inference machine. So how does this work? This is an example from the test set. And in the yellow curve, yellow dashed curve, you see the reconstructed spectrum using our recurrent inference machine. You can see it does a really good job at recovering the spectrum. Of course, this is just one example from our test set. I'll show you some more examples. So keep in mind, if you look up in the top right, we have our observed spectrum. So what happens when we go from our observed spectrum to our true spectrum? Now, what can we do? Why are we even doing this deconvolution in the first place? Well, It allows us to stack our X-ray spectrum from all the different epochs for the first time ever. We've never been able to do this before. It allows for the direct study of transient X-ray sources without having to worry about your response matrix. We have been using it to derive the Chandra calibration and look for potential errors in Chandra's calibration techniques using this recurrent inference machine. And really, with these deconvolved spectrum or these true intrinsic spectrum, we can use these for a whole host of different machine learning applications, such as parameter estimation with neural networks. In this last slide, I'm just showing a bit of the zoology of the different spectrum. So you can see the observed spectrum, of course, these are the convolved spectrum, very difficult to pull out any features. And you see in the blue curve, or in the yellow curve, the prediction from the recurrent inference machine. You can see for the most part, it does an extremely good job with some exceptions. So if you have any ideas about how we could use this recurrent inference machine for your problem, or how you might be able to use the deconvolved spectrum, please let me know. Again, my name is Carter Ray, and thank you very much for listening.